We have a really exciting presentation now. Working in Europe, there's a lot of interest in hydropower research and fine-scale positioning units, and I've had the good fortune of meeting Henrik at several meetings over the past couple of years and seeing firsthand the work that he's done to really advance the state of some of our analysis tools that are available to us. And when we organized this workshop, we had to really identify that we wanted to include YAPS, the program that Henrik has written, as one of the training workshops that we were going to run, and we begged Henrik to come and give this workshop himself, because I've seen him give it before, and I've seen firsthand the advancements that it can make in people's research programs when they have these tools available to them to analyze and resolve some of their positions. So thank you so much for coming, Henrik. I know this is your first time in North America. You came a very long way to come and be with us, so we all appreciate it. Really looking forward to your talk, and yeah, thanks again.
Okay. Is it good? Is it too high? It's good. Okay, thanks a lot, Robert and Kim, for inviting me here today. As Robert said, this is going to be about positioning, and it's going to be about a package that I have made together with some of my great colleagues, some Norwegian guys, Carl Gjelland and Finn Økland, and Torbjørn Forseth from Nina in Norway have been very important in getting this off the ground. And also Uffe Thygesen, my colleague from DTU. He used to be in DTU Aqua, he's now DTU Compute. He has been very pivotal in getting this to work. Right. A disclaimer, I'm a fish biologist, and this is all about statistical models and stuff. And so this is me doing statistical modeling sometimes, it seems. But luckily we have experts in that in the room. Kim is a huge expert on statistical models and has also seen a bit of the YAPS package, so she knows what it is and can jump in if we get into too deep water. Just to make sure we are all on the same page here, this is about 2D and 3D telemetry. And it's, I assume you all are pretty well familiar with the idea, but of course we put out an array of hydrophones, tag some fish, and then we want to get a track of the fish whenever it's inside or near the hydrophone array. That's the whole point of this. So this is a more schematic view of that. We have the tagged fish somewhere within the area. We don't know where it is. That's what we want to find out. To use this, we utilize that the speed of sound in water can be estimated very closely with this equation here, and this means that in fresh water at 10 degrees Celsius, for instance, the speed of sound is approximately 1450 meters per second. So it takes the sound 0.0007 seconds to travel 1 meter, so we are talking about very, very minute timestamps here. All right. So we have our fish swimming around in the array. It emits a signal of whatever type, and it gets picked up, in this case, on 3 hydrophones at time t1, 2, and 3. Then, traditionally, you would use a time difference of arrival method to estimate where the fish was at the time of ping. And the principle in this is that you take the time difference of arrival between 2 hydrophones and get whatever number out of that, and then you can make a hyperbolic curve representing this exact time of difference. So anywhere along this curve, there is the same time of difference in arrival between this and that hydrophone. And you can do that between all the pairs of hydrophones, and then you get something like this. These are the equations describing those hyperbolic curves. And if you solve them with regard to x and y, you know exactly where your fish was at the time of ping. At least that's the theory. So this is what have been done up until recently. It has been pretty much the only way of doing it. But there is another way which is based solely on time of arrival instead of time difference of arrival. The rationale is pretty much the same, that you have your fish pinging being detected by hydrophones, but instead of hyperbolic curves, we have these circles here. describing the time difference of ping towards time difference of arrival. And you can see the equations are a lot simpler and it's all good. The caveat to this is, oh, yeah, it will come. Anyway, so we have these two fundamentally different ways of doing it, time difference of arrival and the time of arrival. For some mathematical and geometric reasons, time of arrival is better. It gives better accuracy and precision, especially as you have your fish moving outside the hydrophone array. The caveat to that is that you need to know the time of ping, so when the transmitter actually emitted its ping. And generally we don't, but we can estimate it, and this is something I will get a tiny bit into. First of all, why even bother using YAPS? Because it's not easy, as you will see later on, but it's doable. No matter which manufacturer you go to, I'm sure they will have a solution for you that will turn your data into X, Y, and Z sometimes. Estimates with some kind of error estimates around your, or on your positions. The thing with that approach is that each of those guys will use a black box to estimate the positions, and they are seemingly very reluctant to tell you what they're doing inside that black box. On top of that, most of, or all the tracks I've seen from manufacturer solutions will need some kind of filtering afterwards. Maybe even two types of filters on the same data set. And the filtering approaches that people are using seems to be dependent on what software has been used to estimate positions in the first place. So the question is, how comparable are tracks estimated with different systems? It's not a problem if you have your own little lake, you have your own system running there and you're happy with that. But if you're in a networking thing and want to compare tracks between studies of the same species, for instance, it might be an issue if it's not the same algorithm behind it. Now, this is one of the nice sides of YAPS, is that it's hardware agnostic. It doesn't matter where your data comes from, be it Vemco, Low-Tech, Telma, ATS, whoever comes next, and whatever they try to do. As long as you have some time of arrival stamps and you have your hydrophone positions, you can throw it into YAPS and get an estimated track out. And this has been tested and approved. I have been involved in several studies where we have used the Vemco PPM 69 kilohertz and the Vemco HR2. Works for that. We have used Low-Tech 76 kilohertz and Low-Tech 200 kilohertz. That works. The Thelma Biotel PPM encoding also works, and also I did a very tiny test track with JSATs from ATS, and it works with that too. Yeah.
Are there any manufacturers that YAPS doesn't work with?
Not that I know of. So the question was if there were any manufacturers that YAPS doesn't work with. Maybe, but then that would be fault of the manufacturer not delivering the data that we need. Okay. So.
Have you ever compared output of YAPS with output of the system on the same data?
Yes, with some of the manufacturer systems. Yeah, we do that when we have the chance to do it, and I will show some examples about that. Another thing that might be a reason to use YAPS over the other time difference of arrival based methods is that we all know you need at least 3 hydrophones to estimate the position of a ping if you use time of arrival, no, time difference of arrival. But as I will show you later today, if you're using YAPS, you can actually do with just 1 hydrophone picking up each ping, as long as it's different hydrophones. You need more than 1 hydrophone in the water, goes without saying. But you will see some quite cool tracks later on. All right, YAPS is open source. You can go to GitHub, look at how it's done. So we're basically opening the black box of fine-scale positioning telemetry in fish. Transparent, reproducible. You can open the source and look for all the bugs that I'm sure is in there. If you find them, please let me know so we can fix them along the way. It's free, unless you count your hours into this, because it's going to take a bit of time. And if not for any other reason, then it actually works. This is exactly an example of that. This is from a Swedish very little pond where they had put out a Vemcore HR2 system. The gray track in the background is the estimated positions from the VPS software, whereas the colorful, it's color-coded by day, is a direct output from YAPS. Anyway, after all, it's only a model. You don't need to buy hardware except a very powerful workstation, perhaps. So the input is hydrophone positions, time of arrival of each ping at each hydrophone. Throw it into the model, and with a bit of luck, it will run and converge, and you will get your estimated positions and tracks. So back in 2017, we published this basic version of YAPS. There has been some improvements to it since, but we'll just stick with this for now. All these fancy formulas I will not go into much detail with, just mention a few features or key components of it. This random walk up there estimates the time of ping. As I said, we need to know time of ping to use time of arrival. This is estimated with a random walk like this. A thing we haven't touched on yet is how to handle errors in such a model like this. If you look at your raw data of hydrophone streaming in, you will get a lot of, sometimes, depending on environment, you will get a lot of echoing, multipath signals, what have you. And if you don't account for that correctly, it will lead to outliers and residuals living out here, where you have your main thing here. And it will drag the position estimates out toward those outliers. In the YAPS, we use a mixture distribution of a normal distribution and a T distribution. And the main reason for that is that the T part of that distribution allows those outliers to live out there without dragging the position estimates. So it's kind of a robust regression applied to this.
Quick question, Henrik.
Yeah.
Outliers in what again?
Outliers in the time of arrival stamp. If you have a multipath signal, it will come in at a completely wrong time, and that will drag it out.
So it's measurement error in the process of when the ping happens to when it actually gets to the receiver.
Yeah, I guess.
Okay.
Okay, and of course we are actually interested in the fish position. This is what it's all about, and we model that with the movement model also. And what that does is basically to keep track of the fish, if you will. If you have a fish swimming here, estimated track is like this. At time leading up to any given event, it's not going to be out here all of a sudden and then back again. So it keeps the fish on its track, if you will. Okay, it runs in template model builder. Some of you have had some issues installing it now, but I hope most of you guys are up and running. We looked a bit upon it before, but this is a track from a Norwegian river where we have the black track. There is a GPS tow track, so we know exactly where the transmitter was at any given time. The blue lines going everywhere on this plot here is the track estimated with a naive time difference of arrival model. So you see all kinds of crazy stuff going on. We had a lot of concrete in this place, so we have a lot of echo and multipath and what have you. If you look in the manufacturer documentation, you will find explanations like this for why the tracks are moving out there. I added one of them out of my own volition. I haven't seen the last one in any. Okay, so to test the performance of YAPS compared to other solutions, we did this track. And again, this was the time difference of arrival model, a very naive one, not doing any kind of filtering or anything, just straight into it, straight out. It looked like that. It's a bit misleading. Most of the points are actually on the black track, but for the purpose of visualization, I added lines between them so you can see where they are. This was a low-tech system. I don't remember, it was 76 or 200 kilohertz. So we had the UMAP software to estimate positions. It looks like this. It's better than the raw time difference of arrival method. But when we apply YAPS to it, it looks like this. So make your choice. This is unfiltered data out of YAPS, the straight output. If you look at the raw numbers, comparing the track, the known track to the estimate track, yeah, Robert?
Can you quickly switch back to the time difference for arrival?
Yes.
So those are the estimates
No, those are the estimates from a time difference of arrival I made. So there's absolutely nothing fancy on that. The low-tech UMAP is way much better than this naive one, that's for sure, but still. Anyway, looking at the numbers of that, you will notice that the time difference of arrival model that we made ourselves gave 89% of the actual pings turned into a position. And that's, of course, the limit to that is the number of hydrophones needs to be higher than or equal to 3. You notice that low-tech UMAP only gave out 80% of those position estimates, and that's a bit, where did the 9% go? That's part of the black box magic. I would like to decide what to do with those 9%. But anyway, YAPS will give you 100% of the track because that's how it's built. And in terms of the accuracy and precision, numbers speak for themselves. Now, this area there is highly oversaturated. We had 28 hydrophones there, so that was really turned out to be a bit overkill, but better safe than sorry. So to try to push the limits on YAPS, we reduced afterwards. We took out 22 of the hydrophones in the data and fitted fitted YAPS to those data, and we got this out. Of course, it's not as good as when we had 28 hydrophones, that goes without saying, but it's still pretty decent. Especially if you look at number of detecting hydrophones for each ping. Only in 36% of the pings were detected by more than 3 hydrophones. So 64 was detected by less than 3 hydrophones. This is the number of hydrophones detecting each ping. So that's decent at least. Another example of that, this is from a German lake, Kleiner Döllensee, some data from Robert Arlinghaus. I've hopefully have permission to show here. In this case, only, you can see there was 16% of the data were detected by 3 or more hydrophones, and the rest had very low detection. This is a fish. I don't know if it's a pike or a perch or whatever, but so we don't know the true track of this, but at least it stays within the lake, and for that it might be might be plausible. I don't know. Okay, so now I have, of course, convinced you all that YAPS is magic, completely flexible, and a turnkey solution, the holy grail of fish telemetry. No, it's not. Sorry. It's not magic if your study design sucks or your data sucks. Garbage in equals garbage out. That's how it is. The internal makings of the TMB model that runs this needs to be differentiable, and that puts some restriction on how flexible we can make things, which I learned the hard way, spending many days trying to get some clever things to work, and then Uffe told me, no, it's not differentiable. Well, thank you. And it's not a turnkey solution. If you try to, or decide to use YAPS, you will need to get your hands dirty, you will have a lot of work. You might end up doing like that guy over there, but this is why we're here today, trying to reduce the risk of that. Right, so before we go further, ping types. I know most people here are working with one particular manufacturer that delivers random burst intervals, and as far as I know, they're not willing or able to share the sequence between intervals. So that gives you a secret random burst interval, right? You have time on the axis, so your transmitter goes ping, 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 with, for instance, 60 to 120 seconds, randomly chosen. You don't know anything. The alternative to that is basically the same random sequence, but now you know how long time there is between pings. These sequences are generated as a random sequence. You can, I guess all of us can make a random sequence of numbers in R in like one line. So this is what's going on. From some manufacturers, you can actually get access to those intervals between the pings, and that gives you extra information that enables a lot better estimation of positions, as you'll see. Finally, we have fixed burst intervals, which, as far as I know, is pretty much only available from low-tech and in the JSAT system. And just to, you have your secret random burst intervals from Vemco, you have known random burst intervals from Telma and in the open protocol. It's available, it's out there, and it's actually working. It's available from low-tech Telma and Sonotronics, and I do not get paid to say this. I say it because I think it's important to be aware that there are alternatives. And another alternative is the JSATs. Tiny, tiny tags. They have injectable tags, and it works really, really well. Okay, what affects performance? And this is with the focus on positional telemetry, of course. The first one, detection range and number of hydrophones. Goes without saying, we've seen this already. One of the things that makes it possible to estimate the track, even though we have so few hydrophones detecting it, is the movement model in the YAPS, and that we have information about when the next ping is coming. These are fixed burst interval transmitters. Array geometry. This is from our paper. This left figure here is the time difference of arrival model. The right one is the time of arrival model. It's simulated tracks, so we simulated a couple of hundred tracks, estimated it with either one of the approaches, and then took the deviation from the estimated to the true simulated position and color-coded it like that. Notice the scale is log transformed. So it's a huge difference between the red and the blue dots in this. You can see as soon as you start getting near the edge of the array with the time difference of arrival, your accuracy and precision just blows up. Whereas using YAPS, you can still do some things outside the hydrophone array. And that goes down to using the time of arrival instead of time difference of arrival. Multipath propagation, this is what ended up in the error distributions out here. This is the thing. What we want is the direct detection from the fish to the hydrophone, not a signal that bounces off the wall of your concrete structures, the bottom surface, whatever it can bounce off of. Even if it do, you can still get decent tracks with YAPS up to a certain point. I mean, if the majority of your data is crap and multipath, then you're not really going to do much with it. And going back again to ping type, and now putting in burst rate as well. There's a lot of thing going on that figure over there, so we'll take it slowly. It's from a paper led by Jenna Vergoinst, hopefully, from Belgium. I'm involved in it. It's a simulation study where we compare estimated tracks to true simulated tracks. You have 5 panels on that plot there. Each of them represents a probability of multipath for each signal. The picture is the same in all of them. It's just the scale that shifts up and down. So let's just focus on one. On the x-axis, we have mean burst interval in seconds. And on the y-axis, we have, of course, a median error for each of the 200, 500 simulated tracks. And what you can see there is if you use fixed burst interval transmitters with YAPS, you get the best performance, the green line. In all cases, that seems to work best, and it makes sense. That's where you have the most information about when next ping is coming. If you know your random burst interval, you do almost just as well. It seems to be tapering off a little bit, but still very good. Whereas if you have secret random burst interval, well, it's basically the worst thing you can have. You have no idea when next ping is coming. All right, yeah. Receiver sampling frequency also affects. That's something for another day. Final notes for this. YAPS is a work in progress. We're working on it, or I'm working on it all the time. It's an R package, as you will see shortly, and it lives on GitHub. Just want to mention that all of this so far has been based on acoustic telemetry, but YAPS will work for other types of telemetry, if you will. I'm collaborating with some bird people that do radio telemetry positioning. I'm not really started on yet, but I suspect it should work. If you have some kind of data collection device where signal power and distance have a clear correlation, we can adapt YAPS to use that. The new roam or Pong technology that's supposed to be out there, where you basically put a hydrophone on your fish, only larger fish, and have some very high power, low frequency stationary transmitters emitting a Pong every now and then. We're talking hundreds of thousands of kilometers range on that. That could go into YAPS. Soniferous animals should go into YAPS as well. needs some modifications, but we will work it. Yeah. Okay, and again, the contributors to YAPS, and of course, no fish telemetry presentation without an animation. So this is back at the Norwegian river. The river flow is like this. We have hydropower intake, as you can see. The dam is there with an open spillway around there. And this is a track of a single Atlantic salmon kelt. The track is totally 22 hours or something, and you see it moves around a lot in that time. This is data straight out of YAPS, no filtering or smoothing or anything. In the meantime, check out this if you want to. This is some work that I have not really been involved in. I helped him get YAPS running. It's a comparison between YAPS and VPS. It's on the GitHub repository for this workshop. All right. Yeah, so exercise time. I'm going to expose you to a few data sets, and the protocol for each of them is basically prepare your data for the synchronization. We'll get to the synchronization. Run your synchronization, obtain a synchronization model, apply that to all your data for the fish, have a look at your fish data, see what they actually look like to make sure you know what you're doing, and then estimate the tracks. Easy peasy. This step here have been causing a lot of trouble for otherwise potential users of YAPS. So pretty much what makes it not a turnkey solution. So we have put a lot of effort into making it as simple as possible. I'll leave it up to you to decide whether that worked or not. What you see here is actually the synchronization model output. This is the drift of hydrophones. So each line there represents one hydrophone and the drift of the internal clock of that hydrophone over time. And you can see it's a bit complex. It's non-linear, it's non-parallel, it's non-nothing. Synchronization, it's in theory, it's basically, it's very simple. You have one timekeeper. You choose one hydrophone to say whatever time this hydrophone says it is, it is. You might take the one with the least drift. That would make sense. So you pick that. And then, skip point number 2, we'll get to that. Then you need to have this timestamp, or this timekeeper, propagate into your entire array. One way of doing it I've seen around is to start somewhere where your timekeeper is, could be there, synchronize the hydrophones within that circle, then propagate it outwards until you have your entire array covered. The issue with this sequential approach is that each time you do this, there will be an estimation error, uncertainty in it, and this can multiply or propagate out through your array. So you end up having the forest hydrophones might not really be good. The synchronization model we have in the YAPS package do it all at once. It just takes whatever data you have and fit a model that makes most sense given the data. And as part of that synchronization model, you can specify if some of your hydrophones, where you're uncertain of the positions of them, you can estimate that as part of the synchronization process. If, for instance, they have been moved since you put them out or whatever. You forgot your GPS when you put them out, what do I know? You need to have, I think, 2 or 3 need to be fixed at known positions, and then you can basically estimate the rest, but bring your GPS. Okay, the exercise is 3 data sets, one from Florida, collected by Jennifer Rehart's group, of which we have one representative here today. He can tell you all about that data set. It's a very tiny data set. It's perfect to check that everything is working and to get a feeling for it. 19 hydros, Vemco VR2, and this is a tow track with GPS, so we know the truth of it. Then, depending on time, we'll do some Norwegian crayfish, 8 hydrophones, Telma Biotel, back from the days when they couldn't really keep track of their random burst intervals. So these are to be considered secret. Also notice they have really, really long burst intervals, up to 5 minutes between each ping. That's, I'm not sure if it's fine scale or high resolution. Anyway, and then some of my own data from a relatively large, by Danish standard, a large lake. 1 week from a large area, we have 70 hydrophones. We have a tow track, so again with GPS, and some fish from pike. And this is recent data, again from Telma Biotel. So it's random, ppm based, but we know the burst intervals. Yeah, and work in progress. There will be more examples included along the way. For fixed burst interval systems, the low-tech and JSATs and some BEMCO via2 data, I will try to get some more example data into the YAPS package. Dataset 1 and 3 is included in the YAPS package now. Code time. Okay, so we will start with the dataset number 1, just to make sure that everything is up and running and we get an idea of what's going on. Hopefully you all installed and got it to working during lunch. Otherwise, it's a bit late now. But you can follow along with your neighbor or on the R notebook HTML pages that is available on the GitHub. The results and output should be the same as in there. And do shout at me if you have questions along the way. I'll probably not see raised hands. Okay, first of all, load some libraries needed. We load YAPS, of course, and then just run this to test that it's actually working. If you get this exact track, it's working. What you see there is a simulated track in black and then the estimated track in red on top of it. So if you get that, fingers crossed, everything should work. So, the SSU1 dataset. Let's have a look at what we got. If I can hit the right key. This is a list of 3 data tables. Hydros, detections, and GPS. All right, they should be pretty self-explanatory. The hydrophone data table is like this. We have hydrophone serial, position of the hydrophones, X, Y, and Z, and the sync tag that is co-located with that hydrophone, and then an IDX column just running from 1 to how many rows you have. Let's have a look. This is a hydrophone array. This is the sync tags that are co-located with the hydrophones in this. Now, the detection table looks pretty much like this, or it looks exactly like this. It originated from a BEMCO output somewhere, and it has been transformed into this timestamp, tag number. This epo column is the epoch, so that's the time of time of arrival stamp here, translated into number of seconds since 1970, January 1st. The frac column is the fraction of a second that is added to the epoch to get the exact time of arrival. Make sense? So this is number of seconds, this is number of milliseconds in this case. And then we have the tag number of the fish, or tow tag in this case, or tow track, and then serial number of the hydrophone. All right.
Henrik, does every receiver in the system need to have a transmitter associated with it, or some not?
No. In this case, only 3 of them have. As long as there is connectivity in the array, right? You need to have all hydrophones need to hear some sync tags that also other hydrophones listen to. You need to have a coherent network, otherwise it doesn't work. Make sense?
And if the tow tags are unknown, random?
It's not really a problem in synchronization. It's when we get to track estimation, it's an issue. Typically because there is so much data for the synchronization. You have so much data from those tags that are just pinging every 10 seconds all along. Sorry, every 10th minute or whatever. It's not a problem for the synchronization. All right, and in this data set, that is a tow track, we have the GPS track of it. So, and now just because I stumbled upon the leaflet package, I want to run this to make a very nice slippy plot of where we are. You can do that. Look at the leaflet package. Look it up. It's brilliant for stuff like this if you need a quick map. Ooh. Anyway, that was a sidetrack. Okay. So now it's time to synchronize this hydrophone array. The two main functions in YAPS to doing this is this get input sync function, and somewhere here we have the get sync model. There's a lot of stuff going into those functions, and I will not go into the details now. It's documented in the preprint we published recently. And in order to get through all the examples, we just need to keep things moving here. This one might be worth mentioning, the timekeeper, so the IDX, the index of the timekeeper hydrophone. And this is the, any hydrophone that goes in this vector is fixed in the synchronization, so it has an assumed, known, and exact position. Anyone not in this vector, for instance, 1, 4, and 5, in this case will have their position estimated. Okay. So we get these, get some input data, and run the synchronization model. And this will take some time. Not much for this tiny data set. All right. Easy peasy. Then we have made a bit of diagnostic plots for this synchronization model, looking at the residuals. This one just takes all the residuals. So the actual measured time of arrival versus what is estimated in the model. And you see, of course, you want it centered closely around 0, which we have here. There is something going on there, but it doesn't really matter. It's a t-distribution that is working internally in this, so you can have stuff out there without it actually affecting the synchronization too much. This other plot here is also nice to get an overview. You have your hydrophone indexes out here, so 1 to 19 in this case, and your sync tag IDXs up here. And the size of these bubbles tells you how many data is in this combination, and the color tells you the median deviation in the median value of the residuals going into this. Actually, yeah, and just to confuse it further, it's the residuals multiplied by 1500 to get it in a scale that represents meters. Okay. So the residuals in this goes from, or the median residuals go from 0 to 0.78 meters, right? As long as it's relatively close to 0, you're in the good. All right, this plot here is paneled by synchronization tag, and you have hydrophone IDX here. Again, it's the residuals in meters. You want everything centered around 0. This plot is nice to see, is nice to use to identify problematic combinations. If you have a combination of a sync tag receiver that is way outside of the 0 line, then you might want to look into those data a bit more. This is basically the same, just flipped the other way around. So now we have a panel for each hydro and the sync tags there. I'm not going into those now, it's not important. So now we have a synchronization model for these data, or for this data set. And then using this apply sync function, we basically synchronize the entire array, or all the data that we have in that, like so. So if we take a look at this, and I'm old enough to be excused from using RStudio, just to make you know. Okay, you can see that we have a new column over there called epo sync. There is, of course, decimals on that. It's just not shown here. But these are the synchronized data that has been added there. All right, then we prepare the data to go into YAPS. We need a We need a data table with the hydrophones with these labels on, HX, HY, HZ. And then we, in this setup, I mean, this part you can code however you want, but I prefer to do it like this. We take our focal tag, the minimum and maximum from the random burst sequence, select the detections. I don't use pipes and stuff, I use data tables, so you can subset your data using this part out here. So these are the data synchronized from this tow track using tag number this. Now, in order to get those data into YAPS, we need to transform the eposync column into a matrix. And of course there is a function for that. Oops. Yeah. Word wrapping. And if we take a look at this matrix we got now, you can see this is basically what it is. You have a column, one column per hydrophone, one row per ping, and then the time of arrival from that ping on that hydrophone. Now, to get this into YAPS, we have another get input function with some different parameters that you can read up on the in the help files and in the preprint. For now, we'll just run it. You can have a look at it. It's a list, a huge list of various bits and pieces. Don't put too much thought into this now. This is what the input to the YAPS, run YAPS function looks like. And we'll run this, we'll put silence false to get an idea of what's going on, if you will. This is what it looks like when TMB is running. Kim can tell you all about what it actually means, all those numbers. I have no idea. What's important is this final call or message here that YAPS converged, and this objective function is you want this number to be as low as possible, and it can be negative and all good. A very basic plotting function is provided. So this is the estimated track from those data, and we have the GPS from it, and it looks like this. Can you see it? It's kind of thin lines. Overall, we get very good correspondence between the GPS track and the estimated track. And if we plot it like this, where we have time of ping on the x-axis and the x-coordinates and the y-coordinates, you can see it makes sense. The black dotted line in the back is the GPS track, red is YAPS estimations, and these bubbles, if you will, here is the standard error of the estimated track. So in this particular part of the track here, we are a bit uncertain about the estimation, but so be it. There are probably too few detections to make good meaning out of it there. All right, so that's the end of the first example data set. Any questions?
How reliant on it is that the GPS at the stations being really correct? Do you want just the best GPS you can get?
Yes.
Yeah.
The question is how good you want your GPS to be to get the hydrophone positions. And of course, it's a bit, if you have access to a high quality GPS, use it, because it's stupid to introduce uncertainty already before you have fish in the system. So use as good as possible a GPS that you can afford.
Would there be any way to identify, like, if the station had unexpectedly moved?
Sorry?
If the station had unexpectedly moved while you were collecting your data?
Yeah, there is. Then we go up to this again. Yeah, it doesn't make much sense in this data set, but we have some functions like this to do the diagnostic plots of the sync model. And down here we have synchronization period. In this case we only have 2 periods because it's such a short data set, but in a real study covering a half year you would have a long time series, right? And so in this you could be able to see if the hydrophone all of a sudden moved, then your errors would pick up all of a sudden. And then you can go in and subset your data and say, okay, so it moved at this exact date, so we treat it basically as two hydrophones. So one is being shut off when it moved, and the other one is enabled after it's moved. Yeah. I need to build in some functions to make it easy, but it's, yeah. I only have that much time. Okay. Sure. There's always one.
So here, we can turn that off. So here.
Where do I do this? I just killed the power. Okay. Hopefully the mic is on again. All right, so next example is the Norwegian crayfish. Data from my good friend and colleague Jan Davidsen in Norway. Again, this is Telma Biotel from before they were able to reconstruct the birth sequences. But the data, it is as it is. So just make sure to reset your R environment to not have any crazy objects lingering around. Load in a bunch of needed libraries. Description, blah, blah, blah. We have been through that. Now, these data are not included in the R package yet. They might be, I'm not really sure. So we need to load them from an external source. They should be on the, they are on the GitHub repository, and if, with a bit of luck, it should work just doing this. Anyone having problem with this? No? Good. Okay. So what we got here is crayfish data. We got receivers, which is the hydrophone as it is. We got the synchronization data in that, and then we got the crayfish, or the detections of crayfish number 34 and crayfish number 35. And then we have the estimated positions from Telma, from a program or software they call Pinpoint. So we have something to compare against this. Again, we need to synchronize the data first, and there is some lessons to be learned in this data. Just have a look at it. This is what it looks like. We have some crazy column names here, so we get rid of those. We set the order. This is again a data table function, I believe. And then we add these two columns, EPO and FRAC. As we had before, you can see EPO is, okay, it doesn't matter. Let's have a look at what we got. The Telma loggers can detect multiple protocols, and they can detect multiple frequencies. So we need to make, and of course there is some spillover or noise or what have you. So we need to make sure that we only use data from the relevant protocol. We do that here. Again, these are old data from, and suffering a bit from a TBR 700 firmware bug that basically meant if the battery ran out because it got too cold, the internal clock of the receivers reset to 2000. And that means that we have a few rows of data here that is corrupt and useless, so we make sure to get rid of those. All right? So this is what we got now. Yeah. And then we, that's it. One thing to notice here is that the hydrophone table that we got initially from Jan Davidsen is in longitude and latitude, and that's good for plotting in, for instance, the leaflet package, but it's not good for running in YAPS. So we need to get it into UTM coordinates. Other people covered that already, so we just do like this. Add this line here at the IDX column. Okay, so this looks more familiar as to what we had previously. Make a plot. Yeah, how to resize things. So this is the hydrophone area here. Our 8, 9 hydros and 3 co-located sync tags. From the look of it like this, it's easy peasy, but if we, now there is actually a reason to use the leaflet package. If we run it on that, you can see we have some difficulties here. Any detections of this synchronization tag on that hydrophone is obviously wrong. And there are some, I think, they can bounce off whatever. I don't know if the sound can curve around this piece of land, probably not. But this line here will also cause issues because this hydrophone can definitely pick up some data from that synchronization tag up there. It can kind of scoot around that part of the land. So there are some issues here to be aware of. The obvious ones, like this, we get rid of straight away. We run this to tell you that, to show you that there is in fact detection of. There is detection on all hydrophones from all sync tags. So even that crazy combination there do exist in the data, whether it's an actual detection of a crazy bounced signal or if it's noise, I have no idea. Anyway, we get rid of those crazy data, so we now have 2 zeros there. Okay, let's have a look at what it's actually, what the data actually looks like. This is, I guess, a what did you call the plot we had in the other session? Abacat plot, yeah, sure. So this is the duration of the study out here. This is hydrophone serial number up there, and out there we have the synchronization tag serial number. And these are the two we zeroed out. And you can see there are other piece of crazy stuff going on. For instance, the end of the study for some reason is variable between hydrophones. I don't really know why that is, but we don't want to struggle with that, so we get rid of everything later than April 1st for this matter. Try again. Okay, so we got rid of that. And then another way of looking at the data, as long as it's from Telma, is that you can make these kind of plots, because their transmitters are programmed to ping every full second. That's what they aim to do. They don't hit the target directly. There is some slight variation around the full second, but it does mean that we can make plots like this. So sync tag in columns, hydrophones in rows, time, date out here, and then these are the fractions of the second. You can see we get some very clear, nice lines in this, but you can also see that in the beginning of the study, something crazy, notchy thing is going on there. And just to make sure we get rid of the first couple of days, first day, I might want to look into what's going on, but often when you set out the hydrophones, there's a period of, when you're still setting them out, you get crazy data, and some hydrophones might need to settle in. What do I know? For this purpose, we just get rid of the data. Then we create this data table detections again, so in the same format as we had before. Make the list of things to go into the, oops, that was not right, into the synchronization model, or basically compile the list of detections and hydrophones. Set all these crazy parameters. For this purpose, right here, we set a seed to make sure that it's actually running, and we run the synchronization model. And this might take time. Any questions? Yes. The documentation and experience. This is part of the reason why I want to include more example data sets, because there is a huge difference between these PPM-based systems and the HR or the low-tech fast interval. Yeah, but well, it tells you to be patient, so please.
It's a good opportunity, it's a good breath, so they can check on people and see where they're at.
Yeah. All right, we are back again. So we got the synchronization model fitted. And if we look, is there issues? Okay, we're good. Okay, if we look at the diagnostic plots from this, you see it's not as good as we had before. We are still centered very closely around zero. Have some crazy stuff going on out there. I actually don't think it matters, but just for the sake of it, we can look into what's going on. This plot might be helpful. You can see the combination of synchronization tag number 8 on hydrophone number 2 seems to be a bit dodgy, causing some issues. However, it's not the one that we focus on now, it's this one, hydrophone 6, sync tag 6 on hydrophone 1. If we look at the data from that particular combination, you see something like this. And to be honest, I have no idea what is causing this. What you want to see in these data are those straight lines. I have no idea what that is, honestly. So might want to look into it. There might be some way to salvage it. At least you could use data from here and out. But for the purpose of this, we just get rid of that combination of hydrophone and synchronization tag. Now another thing might be sync tag number 3 on hydrophone 5. If we go back to this, no one can remember what that combination was. Anyway, if we look at the plot, what is not really visible here, but I know it exists, is that this combination of sync tag and hydrophone is not a tight, it doesn't give tight lines, it gives kind of wobbly lines. It's not really visible in this plot. It's better in the documentation, I think, or in the R notebooks. Just make some temporary table here to show you what is causing this. So this is the exact sync tag hydrophone combination we're referring to. You see, these plots are there are a bit calculation going into it, but what you want to see is something around 0. What you see here is something around 0 and then some bands out here. And the scale on the y-axis is, again, it's the milliseconds multiplied by the speed of sound in this system. So this corresponds to something crazy is going on at around 30-50 meters. If you look at the map, and now I remember, it's the combination of this synchronization tag to this hydrophone. And what I suspect is happening is that the signals, most of the signals go the straight line from there to there. But some of them might bounce off this structure, whatever it is. I've never been to this site, so I have no idea. But if this is concrete, and some of the signals bounce off and into the hydrophone, this is multipath. And that will give you these bands in the data. It's just a suggestion. I don't know if that's what's going on. Anyway, we get rid of those data. There is enough data to go around, so we get rid of those. Then we have made a note on sync tag 8 on hydrophone 2. This is sync tag 8 as far as I remember, and this is hydrophone 2. And there might be a straight line here, but this piece of land might do something. At least there will be shallow water there. And if you have your your signal going over shallow water near land, all kinds of crazy things might happen. So for the sake of it, we just get rid of that as well. Sync tag 8 on hydrophone 5. 1, 2, 3, 4, 5. It's this one down there. Don't remember why I picked that one up. Ah, yeah. Basically, there are no data to work on there, so we just get rid of them. There will be a functionality in the package to get rid of these combinations where we basically have no data. It will just clutter up. It's not there yet, so we get rid of it. So we're ready to refit the synchronization model finally. We package everything up as before, set a seed for the purpose of making sure it converges right now. If you don't set the seed, you might have to redo it once or twice. There are functionality in the pipeline to do this automatic for you.
Henrik, how do you decide on the number you use for your seed?
Well, I start at 1 and then count up. No. Unfortunately, it doesn't always work with that number, so there are different variations. Yeah. On the plot or what? Yeah. This plot was from the combination of a specific sync tag and hydrophone. And this, of course, is a timestamp. And this is the fraction of a second from detections in that particular combination. The idea of this plot is basically, or the message of it is just to show that the amount of data in this particular combination is very, very low. We basically have no data to fit the synchronization model. And so to not cause issues internal in the synchronization model with having combinations that have just a tiny bit of data, we just get rid of it for now.
And if you have the parallel lines, then
Well, the parallel lines is just a visualization of the data. So where we could see the parallel lines is just that there are data there. The sole purpose of this plot is to show there are no data in this particular case. Okay, and you can see we actually have made some additions to the package that take care of crazy stuff for you. So in this iteration, it found some extreme outliers and got rid of them. And now Mind Manager tells me to update. Not now. It's a fraction of seconds. In the case of ppm data, it's milliseconds. In other systems, the HR2 and the low-tech, it can be, the temporal resolution is much higher. So it's basically just a fraction of a second, going from 0 to 1 with whatever, how many steps there is available in that system.
When you see weird squiggly lines.
Sorry?
That's the problem.
Sorry?
When you see a squiggly line, like we looked at before, TS versus frac, you said there's something weird going on with squiggly lines instead of being straight.
Yeah.
That indicates problems.
Yeah, potential problems. In that case, it was to give a hint to this multipath band to bring that up. But you have, I acknowledge you have to look really close to see that. But be aware that those lines are only available from Telma data, and if using fixed burst interval, I would assume it. Yeah, they should be there too. Okay. Was there more questions? Good. We got ourselves a synchronization model. This plot again, well, we got rid of whatever was going on down there, out there, and yeah. It is what it is, might be room for further improvement, but if you remember, before this number was much, much higher. Now the maximum median error is equivalent to 2 meters. So that should be good for now. If we make, yeah, again, it's the same as before. It's just, you want, in these plots, you want things centered around 0. If you got stuff going on not in 0, then you have some issues. That you might have some issues. Again, it's a t-distribution behind this, so a single thing out there might not be a problem, but just get rid of it for the sake of it. Okay, we apply the synchronization model to our data and do some column gymnastic to it and make a plot of, yeah. So these are still the synchronization data we're working on. And it's basically a visualization of the amount of, what's the word I'm looking for? The amount of correction needed to each hydrophone. You see hydrophone 141 needs a lot of correction. The timekeeper is this guy, so it needs 0 correction. The other ones need variable amount of correction. If we take a look at the fraction column of the non-synced versus the synced data, get something like this. See some crazy stuff going on there still. These are the unsynchronized data. If we take the synchronized data, it looks nice and neat like this. And in this case, you want to have your lines looking like this. The distance between the lines here would represent, the vertical distance represent the distance between the hydrophones in some weird abstract way. Think about it, makes sense. Okay, we got our data finally. We got our synchronization model finally. Now it's time to actually look at some crayfish movement. We take crayfish number 34, and put into this object here. Again, we have crazy column names that we don't want to use. Do a bit of massage, getting rid of wrong protocol detections and wrong timestamps that goes back to 2000. Make a temporary data frame just to show you this, which again is one of those plots I don't remember. So this is the plot for crayfish number 34, we have the time out here, hydrophone up here, and then the number of detection grouped by hour. Okay. We apply the synchronization model. Again, we get this column eposync. Out of that, notice that we have some NAs here. That's because those data are outside the duration where our synchronization model is valid. We don't want to extrapolate beyond the boundaries of the synchronization model. In this case, they'll just get N8 to make sure. Get rid of those, make some plots. Again, this is, what is this? This is the unsynchronized data. And here we have the synchronized data. And be aware that this is, the lines are not as neat and parallel here as in this, the synchronization data, because this is a moving animal. So you see it actually do some shifts here. This is because the animal is moving. So the between hydrophone temporal differences, whatever, will of course vary as the animal moving. Yeah. Okay, getting everything packed up. Taking a look at the number of detecting hydrophones. In this data set we have, I've subsetted the data set somewhere in the code because it would take forever to run on the full data set. At least it would take the rest of this, of my time. You can see we have some issues here. We have long periods of 0 detections. That's not really good. So for the purpose of just moving on, we take a subset of the data. I think it's these guys there. Because remember, this is random burst interval with unknown or secret intervals, so we need to have a decent amount of data available to do something. So we subset it in this line with those ping numbers, 25 to 3500. And this plot is a plot of the well, basically, this is time difference of arrival on the various hydrophones. And again, it's a moving animal, so you can see there is some stuff going on there. It's all, in this case, taking relative to hydrophone number 4. So relative to number 4, the animal is moving around. Okay. In this data set, we have 71% of the pings being detected by more than 3 hydrophones. And we make a plot of that just to show how it looks. Again, ping index out here and number of detecting hydrophones. All the individual pings and then a running mean of, with a window of 100. Yeah, the time of arrival matrix looks like this. We set a seed and the ping type, in this case, is the same as before, random burst interval with unknown. Oh, don't do that. And we just get it running. It will take some time again. Question time? No. How long time do I have, Kim?
I think you have another 15 minutes.
That's not enough. Someone stole my first 15.
You can have another 15 if you want it, for sure.
I would.
That was 100% my fault.
We are not pointing fingers here, Robert.
Number one duty of mine was timekeeping.
All right. Yeah, so again, this is the template model builder running, doing its thing. Don't ask me. Yeah. We converged and we got some crazy warnings, and yeah, in this case it is just warnings. Ignore those. I'm working on filtering those you need to worry about and those you don't need to worry about. Make a quick plot. Looks like this. The black line there is from the Telma pinpoint, and the red one, can you see anything at all? It's very tiny. Okay, yeah. So the black line was from pinpoint and the red one is from YAPS. And there's good correspondence. It's free-ranging animals, so we have no idea which one is the right one. Okay, what do we do? Yeah, make a plot looking at the, again, time of ping. We have the x-coordinate and the y-coordinate and the number of observation or number of detecting hydrophones for each ping. And you can see there is at least somewhat correlation between when the number of detecting hydrophones go down, the errors go up. That makes sense. And sometimes we have some crazy stuff like this. Oh, not sure what it is. All right. Now this was a tiny subset of the entire data, and it would be nice to just try to run YAPS on the whole data set, but giving this period and perhaps this, you might want to split it here and get rid of all the zeros, because we have no data, so we don't know where the crayfish was. So split the data set, run this as a part, this, and perhaps the rest. In theory, and if you try long enough, you should be able to fit the entire stream at once, and you'll just get huge errors in the times when there are no detections. Any questions to crayfish? Good, we know all about them now. So, final data set. These are some of my own data from the larger lake. We have a tow track and we have a pike. And we need to hurry up a bit, but it's the same again and again. You've seen it now, so we don't need to explain that much. Notice here that we source a file here called helper functions. Just some functions do some plotting and stuff. Blah, blah, blah. Oh yeah, the thing here is that in this object we have, in this object containing all the data, we have this guy here, burst sequences, which is the known sequence of pings. And if you look at them, there is one for each pike. It's basically just a stream of numbers, integer numbers. They're very long because the data I selected was somewhat in the middle of the study, so we have a huge list before we actually get to them. Never mind. Making a plot of the array. It looks like this. You've seen that before. We already covered how to run the synchronization model, and given that this array is larger, it will take more time. So I've already ran that synchronization model, and it's included in the HAL object here. You see we have sync model, so we'll just use that for now. Take a look at this. Looks decent. This one gets more interesting as we have a larger array. Again, we have hydrophone index and synchronization tag index up here. And you can get a nice view of who is detecting who and how the network in this lake seems to be working. Yeah. And in this data set, I left out 2 hydrophones from this fixed hydros vector to estimate positions of them, because this one had definitely moved. The other one I was very uncertain about. If we look at these are the GPS positions and these are the estimated positions. So we can see hydrophone number 32 has moved substantially between where we thought it was and where it actually was. So we of course use these new estimated hydrophone positions when we apply the synchronization model to the data.
Really quickly, would there be any benefit to kind of working through that to estimate the differences in positions for your model before calculating, or just assuming that they're all fixed?
Well, if you assume that they're all fixed and it turns out that one of them had moved, you would see in those agnostic plots that combination would have a huge error. And if you run this plot where you have them over time, you would see that all of a sudden it goes up. And that's how I figured out that that one there was something dodgy about that. Okay, so we start with a toe track, and this is a crazy plot. I should probably not forget this. Look at this and say, this is something we know already. This is the ping index of the toe track. It's very, very boring to make toe tracks, so it's not really that long. This is number of observation detecting it, number of hydrophones. So we get this running and keep talking along. This particular transmitter that we used for the toe track had a fixed burst interval of 10 seconds or something. So we have a very good data available here. Oh. All right, it seemed to work out. We make a plot, and you can see everything is going on down here. Again, it's very boring to sail around making toe tracks, so we wasn't too good at it. We're zooming in on that. Somewhere in this plot, you have a black line in the back, which is the GPS, and then a red line, which is the YAPS estimation. Oops. If we look at X and Y again separately, again, we have both the GPS and the YAPS on this plot. This is the X coordinate versus time of ping, and the Y coordinate. And on the red line, there is, in theory, also the error estimates, but in this case, they're very tiny compared to the scale, at least. This is a plot of the error estimates, the standard error of each observation versus ping index, and you can see it. The unit here is meters, so it's, at least the model seems to think that it's doing very well, and from the look of it, it seems to be correct. And now it's getting a bit pressured on time.
Don't worry about it, Henrik.
Yeah.
I'm keeping the time.
Oh yeah, I forgot you were in charge of that, Rob. I'm good. Okay, so as I said before, this is fixed burst interval transmitters, but how fixed is it actually? This is a plot of that. This is just a plot of the, I take the difference between individual pings, so time difference between pings, and subtract the mean of that, and times multiplied with the speed of sound. So this is the variation in ping interval for this fixed burst rate plotter transmitter. The idea here is to show that it is indeed very, very fixed. I mean, this is in meters converted to meters. So the variation caused by the transmitter not being stable in ping time is something like 5 centimeters, so millimeters, wherever we are. All right. In this model, we estimate speed of sound, and we can use that as kind of a sanity check to see if we are doing well. So this is the estimated speed of sound in the model, in the YAPS run here, and this is what the speed of sound actually is at temperatures 15, 16, 17 degrees, which was, of course, the water temperature in the lake at that time. And it makes very good sense. You can use it as kind of a sanity check. A plot of the residuals, if you will, from the model, again in meters, everything is nicely centered around 0. We have some crazy outliers here, which is multipath echo, false detections, what do I know. But we are using a t-distribution or a mixture distribution in this, so these guys doesn't really pull much on the track. All right. Now, we were supposed to downsample this into 3 hydrophones. We can do that. So basically what I'm doing here is to sample the data set. Remember, we had a lot of hydrophones detecting each ping. So now we downsample it to a maximum of 3 hydrophones detecting each ping. rerun everything. And again, you can see we get quite good correspondence between the GPS and the estimated. So of course we try to go even further down. So now there is a maximum of 1 hydrophone detecting each ping. Some of them are not detected at all. We run that. This is where you want to set the seed because it doesn't work every time. But again, we get pretty close to perfect correspondence. Now, comparing the error estimates of those different runs here, this is where we have all the data, and this is where we have maximum hydrophone of 1. This is not the error estimate, sorry. This is the x coordinate and the y coordinates. The tracks are identical. This down here is the error estimates. Of the full data set, you see the error estimate is 0.5 meter. When we go down to maximum 3 hydrophones, it starts to grow up. When we have only 1 hydrophone, of course it gets worse, but still within reason, I would say. Especially considering the scale that this system is working on. We are not really going for sub-meter accuracy here. It's a huge lake by Danish standards. So anything within 2, 3, 4 meters, I'm more than happy with.
Henrik, just so you know, you can have another 15 too, until 3.
Okay. Yeah, well, sorry for ruining your break, but just have to stick with it. Okay. Well, that's about it for the tow track. Now it's time for some actual fish movement. Yeah, I think we're gonna... This first pike here had a transmitter with very fast burst interval, 10 to 30 seconds. And the idea in this code is to first assume that the burst interval is secret or unknown and see how that performs. And then, of course, utilize the information we have and compare the two. But we do the same with the next pike, so we'll just go with that. So I can find it. All right, so this is the other pike. Again, we start by assuming that we don't have any information about the burst sequence. This one is 60 to 120 second between. Grab the data, set the parameters, make a plot. Time on the x-axis, hydrophone index on the y. And of course the colors tells us something about number of detection within each hour. And you can, from this you could almost, if you know where the hydrophones are, you can basically tell where it is. Anyway, we get some YAPS running. First we look a bit at the number of hydrophones detecting each ping. You see, we're not really doing too good here. We're 0, 1, 2, 3. A lot of the running means, the lines here, goes below the magic number of 3, so it's a bit challenging. And this data set is approximately 10,000 pings long, so for now we just take the first 1,000 pings, which would be something like this. So we got a period with very low or relatively low detection, and another one there near the end. And yeah, so this is a close-up of that. Got some pretty unknown whereabouts there, some more there, and something in the end. The number of pings that were detected by 3 or more hydrophones in this subset of the data was this 44.6%. So, without more talk, we just run the model with the magic seed. Questions?
I'm wondering if there's sort of like a lower limit for the number of transmissions that you think you can get a valid track. You know, if there's none, you can't get a valid
Yeah.
model,
There is a limit, definitely, but it's not easy to put a specific number on because it depends on which hydrophones you get picked up on when you actually get picked. If you get picked up on multiple different hydrophones, you can get away with very low number of detections. But if all your detections, if you have 2 detections each time, if all of those are on the same 2 hydrophones, then you have much less information to build the track around. And then it gets more. So basically it's a matter of trial and error if you have low density data and see what happens. But of course, if you have information about when next ping is coming, you are in a much, much better state. Okay, so this worked. Again, we get some crazy warnings. I need to do something about that. This is the track, estimated track. The pike is moving happily up around here. And even though it looks like it's gone on land, if you look back at the map, this is actually in the lake. So there's no problem there. Yeah, the X and Y coordinates, you can see the error estimates is really visible here. This is the periods where we had less than 3 hydrophones detecting each ping. The same for the Y coordinate. If we look at the uncertainty estimates, you can see down here is the number of detecting hydrophones, and when this goes low and we have no idea of when next ping is coming, of course the estimation error goes high. That goes without saying. Okay, but we actually do know the burst sequence of these. So now we try to run the same data but utilizing those this knowledge. And for that to work, we need to align our detections with this known sequence of bursts. Luckily, there's a function for that in the YAPS package. And if I can hit the right button, it will run. So what it's doing now is that it takes a subsample of consecutive detected pings and runs along the whole known sequence of bursts and comparing the differences, and then it identifies this one to be the starting point of this particular data set. Don't mind the other plot, we won't need that for now. So now that we know where our data is on this long list of random numbers, we can utilize this information, build our TOA matrix, get the input up and running, get the input and get it into YAPS. And Robert is not looking at his clock yet, so I'm in the good. So remember, before we estimated this track assuming we didn't know anything about when next ping is coming. Now we estimate the same track based on the same data, but utilizing the information we have about when next ping is coming.
Did instances of a fish not being detected when that ping was set, like if it left the array for a amount of time, does it only influence the time when it's gone, that it just doesn't draw the track there? Or would it also have repercussions for later?
Yeah, I guess that depends on how large a proportion of time it's absent. Yeah. If it's absent the majority, it's actually a good question. I don't know the exact answer. You can, I'm just paddling here, but I would think that if you have too much absence, it might influence the overall. But in that case, you would just cut your data set and exclude those periods where you have no information. You won't. You don't know anything. You will just get. In that case, you will get an interpolation between the last known and first known, and then have a huge error around it. Oh. So we make the plot again, and you see it looks luckily pretty much the same as before. Now, if we look at the uncertainty estimates of this, so this is basically the difference between knowing the next ping, or when the next ping is coming, and not knowing in this particular data set. Over here we have the unknown secret, and here we know what's going on. There are still huge error estimates on this in the period where we have literally no information, makes sense. But overall, the level of uncertainty is much lower when we have information available. Now, this track is something like 10,000 pings it can be estimated using this code if you want. If you're lazy, you just load the track and it looks like this. And all of this is inside the lake, and this is unfiltered data straight out of YAPS. And yeah, this fish moving back and forth. All right, so that's about ends up the coding session. Just have a few final remarks in the PowerPoint. Summary. Hardware agnostic. Take whatever system you're working on. There are pros and cons to each of them. Some give you more data than other. Throw them into YAPS and you'll get estimated tracks out of whatever quality is available based on your data. To get the best quality data possible, know something about when next ping is coming. I assume that point is made clear by now. Use YAPS if you want to get the best out of your data. Again, comparison of the HR2 VPS and the low-tech UMAP versus YAPS. We've seen them before. Get the most out of your data if you have information available at least. Saw that before. And still, it's work in progress, so things change and new functions are added and some might disappear, and I'm trying to make it backwards compatible, but the code might break every now and then. So be it. Stay up to date on the GitHub repository or on the ResearchGate project with this very nice long link. Get in contact when you run into trouble via mail or Twitter handle or whatever. And just to mention some of the things that are in the pipeline for the YAPS package, we'll have more examples thrown in so you have more to start from based on whatever systems you're working with. And if some of you have tow tracks available with GPS, I would love to have a look at them and perhaps throw them in the package if there are good lessons to be learned from them. We're working on better help files and more meaningful error messages than just NA. Doesn't really make much sense. I'm looking into some kind of pre-flight data checks. The TMB model is very picky about the data types you throw in at it. It doesn't work if you throw factors in where it's expecting integers. And at the moment, it will just basically tell you you're an idiot without any further help. So a pre-flight data checks will come in. I will look into put a wrapper around it to run it in parallel. If you have a large study for half a year, whatever, with 100 fish, you don't want to sit and do it manually 10,000 pings at a time. You want to have it kind of automated, and you want to run it in parallel so you can utilize all the computing power of your laptop. I would recommend getting a workstation that you could just sit running for a couple of days to get you the tracks. We're working on a function to sample from the estimated tracks, because what you get out now is the most probable track and the associated error. We're working on a way to sample from that to give you basically a distribution of tracks that will tell you where your fish most likely was. Does that make sense? Good. And later this week, Kim and I is going to work towards a combination of a hidden Markov model and YAPS into one go. All right. You're off. Thank you very much for listening.